Hi everyone, today we're going to talk about 1.3 notes. We are going to learn how we can identify a function if it's even or odd. And also we will learn how can we explain the end behavior of a function. First of all, let's see what is a symmetry. These are some keywords that we're going to use today. So we want to see what is symmetry. Symmetry means that one shape becomes exactly like another when you turn, flip, or slide it. For example, here you see this word, this letter A. If I flip this, or even basically if I fold it over this line, I will see that the two sides are going to be exactly like each other. So I can say this is symmetry to this line. End behavior is defined as what is going on at the end of each graph. That means, like for example, if x is going to infinity, what is going to happen to y? If x is going to negative infinity, what is going to happen to the y again? So as one variable goes to infinity number, extremely large number, or extremely small number, what is going to happen to the other variable? For example, here, if I have a graph like this on my coordinate plane, by end behavior, I mean actually what is going to happen to this end of my graph, or what is going to happen to this end of my graph. So that's about the end behavior. Now let's go to the topic over here, even functions. If a function like f of x is equal to f of negative x, then we say f of x is an even function. Before going to the detail of this part, let's see what does the graph of an even function look like. The graph of an even function is symmetric about the y-axis, like this one that you see here. So this is y-axis over here, and these two sides of the graph on the left and right side of this y-axis are exactly like each other. They're a mirror of each other. So we say this is symmetry to the y-axis. If a function is symmetry to the y-axis, then we say that's an even function. So we say this means that the both sides of the y-axis are mirror images of each other. So that's about the graph. Also, it means that if a point like A and B, for example, this point is on the graph, so is negative A and B. That means on the other side, mirror of this point, which is going to be here, will also be on the graph. If this side is A and B, mirror of this, or symmetry of this point to the y-axis, will be negative A and B. So we say if A and B is in the graph, negative A and B is also there. So here's an example, f of x equal to x squared, and we graph the function as I just told you, it's symmetric to the y-axis, so it will be an even function. So if I have a point like 2 and 4 on my graph, negative 2 and 4 is also going to be on the graph. Now, let's see what is f of negative x. If my equation is f of x equal to x squared, f of negative x is going to look like this. Wherever I see an x, I'm just going to replace that with negative x. So my equation was supposed to be like x squared. Now instead of x, I'm going to put negative x squared. Now let's evaluate this. Negative x squared will be negative x times itself. And we know that negative x times negative x will be positive x squared. And as you see, this is exactly the original function. It's equal to f of x. So because f of negative x is equal to f of x, we say this is an even function. So that's what I meant over here when I said f of negative x equal to f of x, then it's an even function. Let's do another example here. So this is my function, f of x equal to 3x squared plus 4x to 4. Now I want to know what is f of negative x. So wherever I see an x, I'm going to replace that with negative x. So I'm going to write 3. It was supposed to be x squared plus 4x to 4. Now instead of these x's, I'm going to put negative. I put the parentheses here to emphasize that this negative x is going to be raised to the power of 2, or negative x going to be raised to the power of 4. Okay, now negative x to the power of 2, as we just said, is just x to the power of 2. So this will be 3x to 2. And then here, negative x to the power of 4 also is going to be x to the 4. Why? Because it's negative x times itself for 4 times. This negative times this one is positive. This negative times this one is positive, and positive times positive is again positive. And we are multiplying x 4 times, so it will be x to 4. So the answer for this one is 4x to 4. And as you see, this is again exactly the same as f of x. So I can say this is an even function. Now, what is an odd function? A function is odd if f of negative x is equal to negative f of x. So compare this with the upper one over here. F of negative x was equal to the original function, f of x, but this time it's being multiplied by another negative here. Then we say this is an odd function. How does the graph look like? The graph is symmetric about the origin. Like this one, for example, f of x equal to 3x. The graph looks like this, and it's symmetry to the origin. What does that mean? That means if I have a point, like this is the origin, okay? So if I have a point over here, the mirror of this point to the origin is going to be on the other side over here, and that's also on my graph. So if you want to find the mirror of a point to the origin, you just need to draw a straight line to the origin and go exactly the same way and the same measure to the other side. So we say this is symmetry to the origin. That means if a point like A and B is on the graph, negative A and negative B also going to be on the graph because it's on the other side. So A will be negative, B will also be negative. Okay. So here the example 3x, we graphed it, and the graph is symmetry to the origin, so it's odd function. If I have a point like 2 and 6 on my graph, negative 2 and negative 6 is also going to be on the graph. So let's see, what is f of negative x? We want to prove that f of negative x is equal to negative f of x. So the equation is f of x equal to 3x. If I want to find f of negative x, wherever I see an x, I'm just going to replace that with a negative x. So it was supposed to be 3 times x. But now instead of this x, I'm going to put negative x. So 3 times negative x will be equal to negative 3x. And we just saw that 3x was f of x. So this is basically f of x. But I have a negative behind that. So it will be equal to negative f of x. And this means the function is an odd function. Okay, let me show you another example, draw another example for you of an odd function. Let's say I have this function, this graph. This graph is symmetric to the y to the origin. Why? Because if I have a point like here, and I draw a line here, and I can find a symmetry of that or mirror of that on the other side. Well, of course, my graph is not very accurate, but you can just imagine it's accurate, and you see symmetry of any point on the graph is going to be on the other side, and it's also located on the graph. For example, this point, okay, again, symmetry of that is going to be here on the graph as well. So by looking at the graph of this function, I can say that it's symmetry to the origin, so it's an odd function. Okay, let's do these two examples. X to the 3 minus x. I want to know if this function is odd or even. So the first thing that I need to do here is to find f of negative x. So you see, on both cases, I need to find f of negative x, like here. And if f of negative x was equal to f of x, I can say it's even. If that's equal to negative of f of x, that will be odd. So let's see what's going to happen to this one. F of negative x. For x, I'm going to replace negative x. So negative x to the 3 minus, instead of this x, I'm going to put negative x. So I'm going to calculate negative x to the power of 3. It's negative x times itself times itself. These two negatives will be positive, times this negative will be negative. So it will be negative x to the power of 3. And then this negative times this one will be positive x. So as you see, this is not equal to f of x. It's not equal to f of x. So that means it's not even. Okay, now let's see if it's odd or not. So in order to see if it's odd or not, I need to find negative f of x. Okay, so I have to find negative f of x. So all I need to do here is to get the function, which is x3 minus x to the 3 minus x, and put a negative beside that. Then I'm going to calculate this. I will distribute this negative to both these terms. Negative times x to 3 is negative x to 3, and negative times negative is positive x. Okay, so what happened here? Negative f of x is equal to f of negative x. These two are equal to each other. So that means we have an odd function here. Why? Because f of negative x was equal to negative f of x. Okay, now let's do this one. Again, I need to find f of negative x. Let's see what happens. So it will be negative x to the power of 3 plus 1. Negative x to the 3 is negative x to 3 plus 1. Okay, so at the first evaluations, I can see that this is not equal to f of x. So it's not even. Now, let's find negative f of x. So I'm just going to take the equation, x to 3 plus 1, and put a negative behind that. Then I'm going to distribute this negative. So you just need to simplify this expression, which will be negative x to 3 minus 1. Okay, what happened this time? Is this equal to f of negative x? No, they are not equal to each other. So f of negative x is not equal to negative f of x. That means it's not odd as well. So sometimes happens our function is not even and not even, it's not even and not odd. So I can say it's neither of them. So sometimes my function is none of them. Okay, let's go to the next part. Over here, we are going to talk about the end behavior. For each of these parent functions, we're going to find the domain and range and also the end behaviors. We have already talked about domain and range in the previous days, so I'm not going to talk about these, or maybe I can talk about some of them. Like the domain and range of this one. Domain is from left to the right, it's going to cover everything, so it's negative infinity to infinity. And range, bottom to top, again covers everything, so negative infinity to infinity. This function is called constant function. Make sure you learn the name of the function. Okay, now what is the end behavior? When you want to talk about the end behavior, we want to know when x goes to a really large number, like if x is increasing, what is happening to y? So look at this end of the graph. As x is increasing, for each of these points that you see, the x value is going to infinity. It's just continuing to increase. What is happening to y? As you see, the function is going top and right. That means it's going to infinity as well. So I say as x goes to infinity, y also goes to infinity. What happens on this side? From this side, x is going to negative infinity because all the negative values are here on the left side. So I say as x is going to negative infinity, what is happening to y? As you see, the y's are also going to negative infinity. They're getting smaller and smaller. So I say as x goes to negative infinity, y also goes to negative infinity. Absolute value function. Domain is negative infinity to infinity. Range is starting from 0 to infinity. And 0 is included, that's why I put a bracket here. End behavior. As x is going to negative infinity, what is happening to y? You see the y values are going to the positive side of this coordinate plane, positive side of the y-axis. So I can say the y's, as x going to negative infinity, the y's are increasing. They're going to positive infinity. On this side also, x is going to increase to infinity. Y is also increasing. It's going to the upside. So for both cases, y is going to infinity. Same here. X goes to negative infinity, y is increasing, it's going up. So I say y goes to infinity. On this side also, the same, x goes to infinity, y goes to infinity. So this will be the end behavior of the function. For this one, and this is a square root function. Domain is from 0 to infinity because it starts from this point, and 0 is included, I put bracket. The same for range, in 0 to infinity. End behavior. When x is going to infinity, what is happening to y? It's going up and right, it's going to the infinity. So I say it's going to go to infinity. But x goes to negative infinity, we don't have that because x is going to stop at this point. So I don't need to write x goes to negative infinity. We don't have the other end side of that. So we stop that over here. X to the 3 cube function. As x goes to infinity, y is also going to positive infinity. It's increasing. So infinity, infinity. X goes to negative infinity, y goes down. It's decreasing to negative infinity. So I'm going to write that x goes to negative infinity, y goes to negative infinity. Cube root function. X goes to positive infinity, y is also increasing. As x going to negative infinity, y is also decreasing and going to negative infinity. So this will be the end behavior of my function. Exponential function. Well, we know that domain is from negative infinity to infinity, and range is starting from 0 to infinity because it's not covering the negative y values, and starts from a point very close to 0 and then goes to infinity. So that's my domain. 0 itself is not included because we have an asymptote here. We have a horizontal asymptote. It's called y equal to 0. Okay, so let's talk about the end behaviors. First of all, let's talk about this side. As x is going to infinity, just simply y is also going to infinity. So this one is easy, infinity, infinity. But how about the other side? You see here, x is going to negative infinity. It's decreasing. But what is happening to y? Y is getting close to this line, which is y equal to 0, but never passes. If it was going here, I would say y is going to negative infinity, but it's not. So I see that the y is just getting close to 0, doesn't pass. So I'm going to say as x goes to negative infinity, y goes to 0. So wherever you have an asymptote, you need to be careful about the end behavior. The end behavior of your graph will be something that gets close to that asymptote. Okay, so let's talk about this one, log function, which is the inverse of exponential function. Okay, so domain starts from 0 to infinity. Why? Because we don't have anything on this side. The graph is starting from after 0 because we have a vertical asymptote called x equal to 0. So starts from 0 to infinity, and 0 itself is not included, so I put a parenthesis here. Now let's talk about the end behaviors. On this end behavior, x is going to infinity and y is also going to infinity. So this one is easy. How about this side? What is happening to x? As you notice, the x is getting close to this line but doesn't pass. So I cannot say x is going to negative infinity like all the other ones. We had x goes to negative infinity. But here we cannot say that because x is getting close to this line. So I'm going to say x gets close to 0. And then what is this positive sign that you see? This positive sign means x gets close to 0 from the right side. Okay, so I'm going to write that here. I'm going to write it here. X goes to 0 plus means x let me write it again, my handwriting. So x approaches 0 from right, or we can say from the larger side. So this will be the end behavior as x goes to 0 plus. What is happening to y? You see the y values are just decreasing forever. That means y goes to negative infinity. Okay. Now, rational function. About the domain and range, we said that wherever we have an asymptote, we're going to exclude that point from our domain or range. So we have a vertical asymptote here, which is x equal to 0. So that means on my domain, I'm going to exclude 0 from the domain. So I say from negative infinity to 0, I have to make a jump, and then after 0, continue to infinity. So this will be domain. Also, we have a horizontal asymptote here. So bottom to top as I'm moving, negative infinity to 0, jump, and then 0 to infinity. That will be the range of my function. Now, what is happening to my end behaviors? And at this end behavior, x is continuing to increase. So x is going to infinity. But what is y value doing here? We have an asymptote here. It's y equal to 0, and your graph is getting close to this line. So I cannot say y goes to infinity. I would say that if my graph was going like this, then I would say y goes to infinity. But now it's not happening. So my graph is getting close to 0. That's what I'm going to write here. On the left side, again, x is decreasing, going to negative infinity. But what is happening to my y? Just look at the graph at this side. Again, this is getting close to 0, but doesn't pass. If it was passing and going like this, I would say y goes to infinity. But now it's not. I see that y is just getting close to 0. So that's what I'm going to write here, and doesn't pass. So make sure to pay attention to the asymptotes. Now here we have 1 over x squared. This is another function. Okay, the domain. As you see, we have a vertical asymptote here. That's x equal to 0. So I need to exclude this from my domain. As I'm moving from negative infinity, I have to make a jump here and then go after 0 to infinity. So I'm going to write domain negative infinity to 0 and 0 to infinity. How about the range? I move from bottom to top. There is nothing covered here. So negative y's are not included in my range. Where does it start from? It starts from 0. But at 0, again, I have an asymptote. That means the graph is getting close to 0. This is a horizontal asymptote of y equal to 0. My graph is getting close to this line, but doesn't pass. So I can say my range is from 0 to infinity. And because at 0 I have an asymptote, and 0 itself is not included in my graph, so I put a parenthesis here. Then, what is happening to my end behavior? When x is going to positive infinity, that means on this side, x is increasing, continuing to go to infinity. What is happening to y? Similar to here, it's getting close to 0. So I say y gets close to 0. On the other side, again, we have the same story. X goes to negative infinity, but y goes to 0. Greatest integer function. What is their domain? Negative infinity to infinity, because it's covering all the x values. But the range is only the integers, because it's not covering these values in between the integers, just only covering the whole numbers. So it's just integers. Now, what is end behavior? As x is going to infinity, y is also going to infinity. Although it's going by like step by step, it's just jumping, but eventually it's going to infinity. The y is always increasing, so I say it's increasing, goes to infinity. And from this side also, y goes to negative infinity. X goes to negative infinity, but y also is decreasing, although it's making jumps. It's jumping to the next step, but still is decreasing. So I say it's going to negative infinity. Constant function. So what is happening here? First of all, we know that domain is negative infinity to infinity, and range is only 3. You need to put this in a bracket, in curly bracket. So because my y value is always 3, no matter what is my x, it's always 3. It's a constant. Sorry, it's 2, it's not 3. I made a mistake here. So I'm going to make this as 2. Okay, so y is always 2 here. Now, what is happening to my end behavior? One of the end behaviors is this one. What is happening to x at this side? X is just increasing forever. But what is happening to y? Y is not decreasing or not even increasing. Y is a constant value, is always 2. So I'm just going to write 2. On the left side also, the same thing is happening. X is decreasing and y is also always constant. It's always 2. Now, let's talk about something else about all these graphs that we just talked. Let's see if they are even or odd. So all we need to do is to look at the graphs and see if they have any kind of symmetry or not. For linear function, oh my god, I said this is constant. This is linear. It's not constant function. It's linear function. And this one was constant. I apologize. This one is called constant function. Okay. For linear function, do I have a symmetry to the y-axis? No, because this side of the graph is not exactly like this side. So this is not even. But we have a symmetry to the origin. Like any point on here and this side has a mirror on the other side. So this is an odd function. This one, absolute value function, it's symmetry to the y-axis because any point here has a mirror on the other side. So this one is even. So just simply look at the graph and see if you can see any symmetry. This one, symmetry to the y-axis. Any point here has a mirror on the other side. So this is even. How about this one? Is this symmetry to the y-axis? No. Is it symmetry to the origin? But if I have any point here, do I have mirror of that on the other side? No, we don't. So I can say this one is none of them. It's not even and not odd. X to the 3. This is symmetry to the origin. A point here has a mirror on the other side. So this is odd function. Same here. Any point here has a mirror on the other side. Symmetry to the origin. This one is also odd. What is this one? Do we have a symmetry to the x-axis? No. The two sides are not equal. Symmetry to the origin? No. So this one is none of them. Same here. No symmetry to y-axis and no symmetry to the origin. This one is also none of them, or neither of them. Is this symmetry to the y-axis? No, because anything on the right side does not have a mirror on the left side, so it's not even. But is this symmetry to the origin? Yes. Any point here has a symmetry on the other side. Like this one has a symmetry here. This one has a symmetry here. So this one is an odd function. How about this one? You see that any point on the right side has a mirror on the left side. It's symmetry to the y-axis, so this is even. The constant function, any point on the right side has a point on the left side. So this one is even. Okay, how about this one, the greatest integer function? This one is neither of them. Why? Let's see, a point like this one, I call that, this is 2 and 1. Okay, this point that you see here is 2 and 1. The mirror of that point is going to be negative 2 and 1. Negative 2 and 1. Let's see. I'm sorry, negative 2 and negative 1. mirror of this point to the origin, symmetry of that to the origin, should be -2 and -1. Is that included into my function or not? So -2 and -1 is here. And as you see, it's not on my graph. Like at the first sight, you might say this looks symmetry to the y-axis, I mean to the origin, but basically it's not. So it's not odd, and obviously it's not even because we don't see symmetry to the y-axis, so it's neither of them. Okay, so this was today's lesson. I hope it was helpful for you. Have a good day.